Hello and welcome to lecture 18 of the course Computational Complexity. In the previous lecture, we were seeing the proof of the Immermann-Celeb-Seni theorem, that was that NL is equal to co-NL. So we saw how given the count of, so we wanted to show that path complement is an NL. That is, given a graph SG and S and T, we should be able to verify, or we should be able to show using an NL machine that there is no path from S to T. So we saw how to do this given the count of reachable vertices from S. So given the count of reachable vertices from S, let's say 10 or 20 or whatever, we could guess 20 vertices reachable from S, none of which being T, and we can verify that these 20 vertices are indeed reachable from S. So now we have to see how to get this count using the NL machine, right? So the count of reachable vertices from S. So that part we did not see in the previous lecture, so let us see that. So first up, we need to see what does it mean. So now what does it mean to say an NL machine, a non-deterministic machine computes a function, right? So here we are trying to see how a non-deterministic Turing machine computes the number of reachable vertices. Right. So we say that an NL machine or a non-deterministic machine correctly computes a function if on each computation path it either rejects the computation path or correctly estimates the function. So let's say the function value is, let's say 100. So let's say if the machine has, let's say, 4 computation paths from root to all of them, so it could reject every path, and one computation path has to, at least one computation path has to output the correct value. So it is not possible, it is not okay to have, so this is okay. Okay, so even this is okay, like you could have something like this, R100, R100, this is okay. However, you cannot have this. That I am drawing on the right side. You cannot have R100, R, let's say 200. This is not okay because the correct value is 100. So in no computation path could you have the wrong answer. You can, even this also is not useful, as you may guess. If all the paths are rejected, it is also not useful. So it should have at least one path which outputs the correct function value. It could have more than one path that outputs the correct value, but everything should be reject or the correct value. This is the meaning of this is how a non-deterministic machine should compute a function. Each path should either be a reject or estimate the correct function value, plus at least one path should give us the correct function value. If all of them are reject, then it's of no use, right? Okay. So now to compute C, so this is the definition of what we are trying to attain. So we want a non-deterministic log space bounded machine that has at least one computation path that leads us to the number of reachable vertices from S. Okay. So how do we compute the number of reachable vertices from S, right? So what we will do is to have this kind of step-by-step process. So we will define a sequence of sets called A0, A1, A2 and so on. A0 is nothing but the number of vertices or the set of vertices reachable from S in 0 steps. A1 is the set of vertices reachable from S in 1 step. A2 is the set of vertices reachable from S in 2 or smaller than 2 steps, and so on. So A0 is nothing but the set S itself, right? Because if we are not allowed any steps, then the only vertex that we can reach from S is S itself. We can reach in 0 steps, right? A1, let's say this is S and S has 3 vertices or 3 neighbors. Then A1 is all of this. This is A1, right? So A1 has 4 vertices, whereas A0 has only 1 vertex, right? And A2 has perhaps more vertices, right? So A0, A1, etc. are kind of A0 is contained in A1, A1 is contained in A2, because each one we say it is the number of AI is the number of is a set of vertices reachable from S in I steps or lower, right? And corresponding to A0, A1, A2, we could also have C0, C1, C2 and so on, which is the size of each of these. So Ci is size of AI, right? And what we want is a total number of vertices reachable from S. So if any vertex is reachable from S, there is a path of length at most V, right, where V is the number of vertices. It cannot be longer than V. Overall we have V vertices, so any path has to be of length at most V. In fact, V minus 1 would do, right? The number of steps cannot be more than V minus 1. So A subscript or C subscript V will give us the actual number of vertices reachable from S, right? So we, right, and our goal is to compute C subscript V, which is which will be the count C, right? So, and again, so we don't compute C subscript V in one shot. What we will do is, so we know C0, which is this 1, and C1 can be computed from C0, C2 can be computed from C1, C3 can be computed from C2 and so on. That's the approach that we will follow. So let us see how, using a non-deterministic log space machine, we can compute Ci plus 1 from Ci. So we know C0 is 1, then we will see how to compute Ci plus 1 from Ci, right? So for each of the values, for each of the vertices V, right, so now we are going to see how to compute Ci plus 1 from Ci, right? So for each of the vertices V, the non-deterministic Turing machine, it verifies if it can be reachable in I plus 1 steps or less, right? So if we can guess a path that is of I plus 1 of length I plus 1 or less, then good. We know that it is reachable in I plus 1 steps or less. But how do we verify that a vertex is not reachable in I plus 1 steps, right? Because maybe we just guessed the wrong path. Here again we will use the trick that we saw in the previous lecture, right? So notice that when we compute, or when we attempt to compute Ci plus 1, we already know Ci. So if a certain vertex, let's say this is AI, and so let's say this is AI plus 1. So all the vertices, let's say all the vertices that are in AI plus 1 but not in AI, there will be a neighbor, or there will be a vertex, let's say U is, or V is in AI plus 1 but not in AI. There will be some U's in AI such that UV is an edge, right? Because if otherwise if V can be reached in I plus 1 steps, then it has to have a predecessor that can be reached in I steps, right? So in order to verify that, let's say some vertex W cannot be reached in I plus 1 steps, how do we verify that it cannot be reached in I plus 1 steps? So what we will do is to actually show that we have explored all the vertices in AI, right? We have explored all the vertices in AI. Let's say we know that AI has 100 vertices. We will say that we have identified all these 100 vertices in AI, and none of these vertices in AI were found to have an edge to W, right? So this edge was not found. So we know that there are 100 vertices, and we found the 100 vertices. None of them had an edge to W. So that means W is not in AI plus 1. This is how we will establish that a vertex is not in AI plus 1. Right? So for that we will have to verify all the vertices in AI. Right? So this is the way we will do it. Right? So for each vertex, we need to either verify that it is reachable, or we need to verify that it is not reachable. So how do we verify that it is not reachable? We need to actually reconstruct the entire set AI and show that none of these vertices has an edge, right? So for each V, we have to check that we have to check all the elements that are in AI and check whether there is a predecessor in AI such that either the predecessor had an edge to V or the predecessor was V itself, right? So V could be in AI also, right? So the challenge here again is that we cannot guess the entire set AI, or we cannot guess the entire set and write it down somewhere, because AI could have, let's say, n by 2 elements, and that storing that requires order in space, or even at least order in space, right? So we cannot guess the entire set AI and write it down somewhere. So we have to kind of, like we have seen before in the case of space bounded classes, we have to make these guesses in a serial fashion while remembering only the little things that are necessary. Okay, so whatever is necessary, just that is what we will remember. So here what we will remember is only the count. Okay, and we'll see how to, using the count, we can verify that. Okay, so this is the algorithm more formally, right? So let us see what the algorithm is. So first we say C0 is equal to 1, right? Which is one vertex is reachable from S in 0 steps or less. Now we are going to see how for each I we are going to compute Ci plus 1 from Ci, right? So for each I, this loop, the for loop in step number 2 is saying how to compute Ci plus 1 from Ci. So we start with Ci plus 1 being equal to 1, because S is always in all these Ai plus 1, right? So remember, Ai plus 1 is a set of all vertices reachable in I plus 1 steps or less, and Ci plus 1 is the size of Ai, right? So always S is a member of Ai or Ai plus 1 for all I. So we can assume Ci plus 1 and start from 1. Now for each node, each vertex that is not equal to S, right, we check whether there is a path from S to U, right? So what we do is we guess a predecessor. Sorry, we do not guess a predecessor. We for each U in the graph, we check whether U can be reached in I steps or less. Okay, and for that we use check path, which we defined in the previous lecture, which is just verifying whether S to U is reachable in I steps. So we are trying to build the set, but we are not building the set and saving it somewhere. We are just going one by one and verifying the count. And at each point, whenever a U is found to be reachable from S in I steps, we are checking whether U has V as its out neighbor, or VU is also, so there is a small typo here, or U equal to V, right? So if one of these things happen, then we know that V is also reachable in I plus 1 steps. If V is not reachable in I plus 1 steps, we actually need to make sure that we have covered all our possibilities, that all the vertices that were supposed to be reachable in I steps or have actually been identified. So whatever I said over here, we have indeed computed all the vertices in AI. So that is done in step number 13. That have we checked that? So we are keeping a count of for each vertex that was identified to be in AI. That running count is D, and we are checking whether D was equal to Ci. So we already know from the previous loop that Ci was computed. Ci is a count of vertices that are reachable in I steps or less. So we are checking whether we found D, or is the running count D is actually equal to the actual count of the vertices Ci, or the number of vertices Ci. If it is not equal, that means some things were not reached, some count did not get checked, so we reject the computation path entirely, right? But there will be a computation path that will actually go through identify the correct number of vertices, and we can, using in that computation, we will correctly identify that V was not reachable or V was reachable. So suppose we found a vertex V to be reachable, then again we start from step 5, which is that D equal to 0, which means we again start from 0, for each, we are again estimating each vertex in AI, right? So every time we are, for each vertex V, we are re-estimating or recounting the set AI. So we are doing a lot of computation again and again, redoing a lot of computation, but that is the only way out, because our space is very limited and we are not bounded on time. So we can afford to do the recomputation because we are only paying by space in this case. So we start from, so in this loop starting from line 2, what we are doing is that with the assumption that we have Ci, using that and assuming that it is correct, we are counting or we are estimating Ci plus 1. So if we correctly identify the set AI, let's say this is AI, and then we know exactly what are the vertices that are reachable in one more step from AI, so we can correctly estimate Ci plus 1. To check that we have correctly accounted AI, all that we need is so we don't keep track of AI, we don't save the set AI anywhere, instead we just save the count, and every time we regenerate AI and we check whether the count is correct. If the count is correct, we can be assured that this computation is correct. So there will be a lot of paths leading to reject, but that's okay, because there will be some path, at least one path, that will lead to the correct computation. Path meaning the computations. And this loop runs till v minus 1, so which means that at the end we will have correctly computed CV, which is equal to, so CV is equal to the actual count of reachable vertices from S if we have not rejected. If at any stage if we return a value, that will be correct. And what are the things that we need to store here? We need to store I, we need to store Ci, we need to store Ci plus 1, we need to store V, we need to store U, right? C0, not C0, I, Ci plus 1, D, U, V, and we also need Ci, right? These are the things that we require. And notice that just to store C0, C1, C2 up to CV, let's say the number of vertices is n, these itself are n values. So we cannot even store these n values because n values itself are n things. We don't have n order n space. So instead what we will do is that once we compute C0 or once we compute C0, C1, C2, and then C0 can be forgotten and C1 can be forgotten. We only need C2 to compute C3. And once we have C3, C2 can be forgotten. And once we have C4, C3 can be forgotten. So we only need the previous value Ci to compute Ci plus 1. And once we have Ci plus 1, we can forget Ci. So, and each of these, so we don't store all the Ci's together. We only need the latest, the previous value and the current running value. And each one of these numbers is either a vertex or a count that is no more than n. So each one of them requires only order log n space, right? So finally the function returns CV. If it has not rejected, it will correctly compute CV. Again, this algorithm, so that is pretty much the Immermann-Celeps-Seny proof. This proof is not so straightforward, right? So because it has this intricate use of non-determinism and recomputing again and again in order to save space. This idea is being used again and again. So there are 2 or 3 key ideas. One is computing again and again to save space, and then non-deterministically guessing a sequence of vertices, right? And then for each one choosing whether it is in the set or not in the set, or not deterministically guessing a sequence to find a path from S to T, right? So for each vertex in the path is guessed one by one. So these are the tricks that are used in this proof. But it is very, very instructive to understand how non-determinism works, and also how space bounded computation works. So what I'm saying is that if there are parts that you cannot follow, please don't feel disheartened. It's only natural because this proof is a bit involved. Please, you can read SIPSR or this notes that I will share, and I had also typed up a PDF some time back, so I can also share that PDF. So the result is that NL is equal to co-NL. So we do that by it is called Immermann-Selepseny theorem. We do that by showing that path complement is in NL, which is to show that we should be able to decide using an NL machine that you cannot reach T from S. Okay. So first we saw how to show this using an NL machine given the count of vertices reachable from S. And in this lecture, we saw how to come up with that count. So we came up with that count by having these counts of the successive sets A0, A1, A2, etc. Where A0 is a set of vertices reachable in 0 steps from S, A1 is a set of vertices reachable in 1 step from S, A2 is a set of vertices reachable in 2 steps from S, and so on. And most of the algorithm was about how to compute AI plus 1 from AI. And we need to store a bunch of variables, maybe 5-6 variables, and each of one of them being taking at most order log in space. Right. Maybe I can be erased. So we have seen some complexity classes. So just so we could have a short recap. Let's say A, or let's say A subset of B, this is denoted by so I am using a right arrow to denote containment. So let me draw the status of the complexity classes as we know it now in the course. So we know that L is contained in NL. Okay. So I am using the right arrow to denote containment. And we know that NL is contained in P. Right. We do not know whether Ln is a strict subset of L is a strict subset of NL. We do not know if NL is a strict subset of P, right? And we saw P is contained in NP. We saw P is contained in co-NP. But between NP and co-NP, we do not know how they interrelate. We saw NP is contained in sigma 2. Co-NP is contained in pi 2, co-NP is contained in sigma 2, NP is contained in sigma pi 2, sigma 3, pi 3. So notice that if P is in NP and NP is in sigma 2, it automatically implies that P is in sigma 2, right? So and so on, right? So you can write pi 4, sigma 4, everything, and so on. And we will see that all of these are contained in P space, which is polynomial space, D space of polynomial. And we already saw in the lecture where we talked about Savage's theorem that in the case of space complexity, P space and NP space are the same. So P space is the same as this. And another point is that NL, in this lecture we saw that NL is equal to co-NL. Right, so this is what we know as of now. And none of these arrows that I have drawn here, we don't know whether any of them are strict or equal. So L equal to NL or L is a strict subset, we do not know. NL equal to P or a strict subset, we do not know. P strict subset of NP or equal, we do not know. NP sigma 2, we do not know, and so on. Anything NP pi 2, we do not know. Right? The only equality that we know is P space is NP space and NL is equal to co-NL. The only other thing that we know is that the left endpoint P space, left endpoint is L and the right endpoint being P space. These two are not the same because L uses log space and P space uses polynomial space. So just like we had time hierarchy theorem, we will also see a space hierarchy theorem in the next week's lectures, where we will show that if there are two if two sufficiently separated functions, d space of the first function is a strict subset of d space of the second function, as long as they are sufficiently separated. So log space is a strict subset of p space, so we know that L is not equal to p space, but then none of these individual arrows we know whether they are strict or not. Again, this is just food for thought. There is so much that we have learned so far, but even in the world of even in the most up-to-date state-of-the-art research, we do not know so many things about these complexity classes, and that's what makes this an interesting field. There are so many things that are still to be known and still being studied and understood with time. And with that thought, I'll stop this. I'll end this lecture 18, and thank you.